I do not have a whole lot today. I know everybody will be sad. Really, I'm just going to go through the one chapter and then we might go over a couple things, but we'll save, like I said, we'll save Monday for, we're going to do the review for the final. And actually, that'll be our last meeting day per se. Tomorrow, we'll have the open lab. So for anybody that needs a free time or something, want to get caught up, or even come in and go over some formulas or anything like that, we can pretty much that's tomorrow. And today will be like I say, today's a short day. We're just really gonna go over the rest of this chapter and just finish talking. It's filters. Chapter 23. It's all about filters. So it's just basically the next step in our RLCs. And in fact, in one of the things that we do go through in here, you'll see that there actually is an alternative component that is pretty widely popular. They use them in a lot on PCs, anything along those lines, where even like your cell phone or something like that, where you need a fixed frequency. But we'll get into that, and we'll show you what the alternatives are. There's a couple of off the shelf. You can actually buy things at specific frequencies, if you will. And really, where a lot of this will come into play, like, well, you'll see from some of the examples we'll go through in here, a lot of this will come into play basically when we go into solid state. So when we go into 134 and then even 135, or solid state and advanced solid state, we actually start using these circuits to provide us with specific signals that we would need for amplifiers and things along those natures. But you might recognize, okay, so if we take a look at this chapter 23, part 7, right? Notice the term there we have, it's resonant. And this is precisely that, just as we were going through resonance. Now, this would be a resonant filter where you would have specific center frequency and then two uh, half power point, basically providing us with a particular bandwidth, if you will. And that's why they would call it a tuned circuit, because it would be, as you've seen from the labs, our bandwidth region that we have overall in resonance is, it can be decently sized, but it doesn't, we really don't have a whole lot of room, right? So a tuned circuit goes along those lines where you would want just a specific frequency. Let's say you only wanted to tune in to like a particular radio band, or if you will. And so you would set up to just receive that frequency only. So it wouldn't have any like changing parts, if you will. It pretty much would take in the frequency that we want. And after the half power points, pretty much reject all other signals. So again, and we would be going through and actually taking a look at the Q of the circuit and make sure that it meets the needs that we want. And at this point, we've used all the formulas. You have those formula sheets, and this will carry with you in the future. So when we do need to set up a specific filter, let's say, and this works in power transmission as well. So if we want to turn, like, let's say, an AC signal to a DC signal, we could use something very much along these lines, because we know what our utility frequency is going to be. It's going to be the 60 hertz. So we can pretty much set it up for that particular frequency and then convert that signal. We won't get into how we're going to convert the signal. That we'll leave for we'll leave for the 134, and then 135 even goes past that a little further. But in 134, we do examine DC power supplies and how we go about converting AC signals into DC signals and vice versa. Um, but they do have a particular name. Now, it can do a few different things. They have, I mean, most particular, the resonant filters are usually like a band stop or a band pass because they are at a particular band. So we could set it up in one of two ways. Either A, we pass that center frequency through, or B, we literally reject that frequency. So let's say we do have a particular frequency that keeps interfering with our signal. We could use a resonant filter, set it up for that fixed frequency and set it up in such a way that it does not allow that frequency to come in and interfere with the signal that we have in mind. And we'll just take a look real quick here at the types they have. Now notice in the diagram they have a load resistor, but what we're more interested in is the part where it shows the series resonant circuit. Now, the particular thing about the series resonant, and notice up at the top, is that we can get the smallest amount of impedance with the maximum amount of current. So as far as a power end would go, this would be something of interest for us. So what we would do is we would go ahead and set up our particular resonant circuit in a series configuration and put that in with some resistive load. It could even be, you know, a machine or something like that. You know, don't always think that these things are just a resistor. It could be an assembly of some sort. There's so many different outlets. It'd be a little hard to list them all, but essentially, I mean, we're doing some type of work that we're going to be going across this resistive load, and in this case, we would be interested in just allowing that particular frequency to go through our signal, and that way no other signals would come through on us, no matter how hard we tried at the input, right? And so this type of circuit, if we desire a maximum current where we're getting full power output, this would be the type we would use. Now, if we take a look at the parallel one, we almost get like I don't want to say opposite, but it is like an opposite effect where we get the full maximum impedance in this case. Now, from a previous one, a series one, we have minimum impedance. And in a parallel configuration, we get maximum impedance. And really, this is our takeaways from this. So it would depend on what we were, excuse me, interested in achieving here. And that's pretty much it. Then the rest of the chapter goes through and looks at special filter types, where these are like fixed assemblies. You could go in and basically buy these off the shelf as is. So if you were to desire a particular filter, you know, for certain frequencies, you could go ahead and get that. And again, notice this, active filters. Now that we don't examine in this class, but what this does is set you up for going into the next class where we do deal with active componentry. Now, what's the difference with that? So far, what we have used is what's known as passive components. They don't get energized separately. What they do is literally sit there and wait. They become energized by the signals that we pass through them and react to that. And that is a passive component. Now, an active component would be something that's separately energized in a circuit, and then the signals are passed through it after that circuit becomes energized, which we'll examine, you know, later on. And that's most particularly with transistors and operational amplifiers. But that, again, like I said, that's something that we'll be taking a look at in the next class. And this is a symbol that they would show, and we won't go real deep into this, but the triangle symbol in the middle is what's known as an operational amplifier. And again, like I say, you'll examine that in solid state and in advanced, more specifically in advanced solid state. But notice the combinations here. What we have are two different RC filters, if you will. And again, they're set up the same way where you would actually do like the time constant, where it would be R times C, and do your calculations with that. And this would be a type of filter that you would integrate with this operational amplifier. And that would be an off-the-shelf type part where you would just basically select, a particular one that fit your response, your feedbacks with your signals that you're using. We won't get into, like I said, we won't be doing the Bode plots. It will be something we will examine, like log graphs and whatnot, in 134. And again, it's just like a slight review going over, just finishing off this particular section. I didn't want to go real deep into this. Frenzel does incorporate this into the end of the chapter, but doesn't go real deep into the complexities of how this component works or anything. He's just showing how these particular ones can be used. And basically, if we look, I mean, in the one style previously, you'd have like a series parallel configuration, and this one's a little more obvious in the parallel configuration. But in operational amplifiers, there is a feedback to this and different controls that go through this. But again, we will not examine that very deeply. Really, all we're looking at, um, well, we're just looking at like different styles of filters that they would have out there, like what their common uses are. But um, for radio frequencies, we can use different types, and like PCs and anything that would need like a timing characteristics. They do use what's known as a crystal filter, and it is exactly that. It's a piece of crystal, a quartz crystal in this case. And what they'll do, and depending on how they cut it, it responds to vibrations. And an interesting thing is if we pass like an AC signal through it, like a sinusoidal, what it'll do is it actually causes the crystal to begin to oscillate. And depending on how it was cut, the size of the crystal and such, it will vibrate at a specific frequency when you have this voltage going across it. So it gets excited, and it won't give out any other frequency than what it is set to. So if you buy these things off the shelf, you want, I don't know, let's say you wanted a 1 gigahertz uh, frequency, you would buy the 1 gigahertz crystal and it would provide you that clock consistently. You don't have to do any other parts. We wouldn't have to go and set up like an RC circuit, with specific frequency in mind and whatnot, and have to deal with any inequities with the parts and such. These crystals will only set at that particular frequency. And just to show, they have like on the right hand side is the crystal symbol, and notice it's just the one single part, where if I wanted to draw or incorporate an equivalent with it, notice on the left, this is what you would have that would be the same thing as this. So cost factor comes into play, size factor. Now I'm dealing with just one component as compared to dealing with 4 components. So there are several pros to using a crystal versus using like resistors and inductors and capacitors. And they do have these out there. And notice, yeah, the Q of the crystal is usually very, very high. So the bandwidth is very, very tight. And it's a very, very nice thing to do. It's good response, repetitive. You don't have to deal with any of the phase shifting and whatnot. And they even can incorporate, like in this case, you'll see the crystals utilizing the capacitors. and that is just to set it up for like cascading frequencies, if you will. But we won't, like I said, we won't get really big into this. This is really just a touch on it to like finish off this particular section. Now, one thing they do use out in like radio and when dealing with radio frequencies is something called a SAW, where it's a surface acoustic wave filter. And it's a built part. They actually have a certain style to them, if you will. So when you get it, it looks like it it basically looks like a piece of ceramic or like porcelain or something like that. It's like a little flat part, but it does have circuitry incorporated into it, so it actually does respond. And so it would be a new type of thing, but we don't we wouldn't get into this. I mean, buying one of these would be something, but it actually just setting up in a lab, but they had their general purpose. They do locked down on specific frequencies and they fall off at a very drastic rate. So the attenuation, as he states here, is very high. So you would basically be passing through your particular frequency, and the fall offs on that would be drastic. So it's really tight, very precise. And yeah, notice they use them a lot, like yeah, on TV sets, cell phones, basically any type of things where you're using media and wireless equipment, so your Wi-Fi and such like that, you would have some type of SAW filter in there. And they're generally like a stand-up part. It looks very much like what they displayed in the on the picture there, where it's like this rectangular piece with little teeth on it, and it's usually like a stand-up piece that's inside of your like your TV set or cell phone or such. But that's really it. They're just listing off the special types. We don't want to get really deep into that. That's what solid state's for. but but basically, so at this point, we know how to we know the rules and the properties of capacitors. We know the rules and the properties of inductors. We should be able to recognize how that phase, if whether we're leading or lagging, and what we would need to do. So if we had like a leading signal, right, or a lagging signal, and what we would need to do to be able to bring that signal into phase, like if it's an undesired effect. Oh, so let's say, if we had like a leading signal and we wanted to bring that in phase with the original signal for power considerations or whatnot, how we could go through and adjust our circuit for that. And the same with the lagging, whether or not we need to bring it, bring the circuit to be more inductive, or whether we need to bring the circuit to be more capacitive. But we should be able to juggle the formulas and be able to get our desired response that we want. And that we will carry with us. I'm not sure when the next solid state. I think it might be over the summer, where you could take solid state and advanced solid state. And then that we go ahead and we'll look at. It begins off with diodes. Basically, we're dealing with semiconductors at that point, so it's a whole separate thing. And again, like I say, it's an active componentry set, and that even sets you up for getting into digital communications, because basically what we deal with as you study transistors, we deal when you deal with integrated circuits, chips, ICs, they are generally made from a series of transistors. In fact, a lot of the names are transistor based. Like when you deal with the most common one, like TTL logic, it's transistor to transistor logic. And you'll find that these are what they consider active components. So like in the case of a chip, you actually apply a DC power level to it. In the case of TTL, it's a +5, and you would incorporate a ground to it. And then it's an active piece that you can go ahead and subject to different signals to get your desired output. The outputs vary depending on, what type of IC we're dealing with. There's numerous ones, but Bob Bloompot does that one, and you would go through and examine ICs. But essentially, that's what solid state leads us up to: how to deal with diodes, transistors, and op amps, operational amplifiers, and what their rules are. These are nonlinear components. Thus far, we've dealt with pretty much a linear response. Overall, the capacitor is somewhat non-linear per se, but overall, it would be considered a linear response. We can get a desired effect from it. And most specifically, the inductors and resistors are very much linear response type devices. But that's what we're looking forward to. So at this point, like I say, so tomorrow we'll come in. If you don't want to come in tomorrow, if all your labs are in and whatnot, it's a free day. So, stay at home, stay safe, and all that good stuff. Otherwise, if I don't see you tomorrow, we'll see you on Monday. What I'm going to do, what I'll be posting over the weekend, will be like a cheat sheet. I don't want to say cheat sheet, but like a list of topics that will be on the final. It'll be a 50-question test. And like I say, I'll set it up. I'll post that on Tuesday. It'll be available, and it'll be available all the way through till Friday. So take that, next week. So take that as time permits, and then and that'll be pretty much it for the class. I think everybody done fairly well through this class. And if you do have any questions, I mean, we could do that now. If you have questions, we can do question and answer now for you. If you have anything you'd like to go over, or go over tomorrow, or go over on Monday. All right. And again, if you have anything, email me. I do try to respond to you as quickly as possible. But yeah, that's really it, gentlemen. I hope you've enjoyed this and our study, and now you should be all familiarized with everything at this point, hopefully. I think everybody's got a good handle on using the lab equipment. And then, like I say, that'll stand you instead for going forward. You'll use the same set of equipment and in all the digital classes that you'll have, like the microprocessor and such. But it'll also stand you in good stead with the solid state classes as well. And that's about it, I think. Anybody have any questions at this point, or? Oh, you guys, let me stop sharing here. There we go. But no, that's really it. Really, like I say, we're very much on track with where we want to be as far as the class goes. So, uh, give all of you should give yourselves a good clap on the back. You did very well. And otherwise, yeah, I will see some of you tomorrow, perhaps. And if not, I will see you online on Monday. And like I say, we'll just go over a review, probably like this, where we'll go over about a half hour, just to give ourselves time to cover anything, and if you might have questions. And I mean, it'll be it's primarily based on, the test will be on the homeworks and such. So use your formula sheets, and get familiar with those. You should be able to, hopefully you should be able to go over your previous homeworks and quizzes. If anything is caught up, DeRay posted me one yesterday where the quiz wasn't coming up, and I believe I fixed it. But if not, definitely let me know, and I'll go through. Sometimes Blackboard is strange, but yeah, you should be able to go through and see your like previous homeworks. If you had a wrong answer, it should have the corrected one in there for your review, so that way you know exactly which answers go for which questions. All right. But other than that, that's really it. Like I say, this filter section in the book, it's that's something that's more practical to be used when we get into solid state, because there you'll actually be manipulating and setting up desired responses, if you will, using these with diodes and using these with transistors, and seeing what they actually can do. But yeah, that's all I got, gentlemen. Looks like a chilly day, but the sun's out, so we'll consider it a nice day. And other than that, yeah, like I say, if you've got any missing homeworks or anything, you should be able to go through and still repost a homework. If not, let me know. It might need a reset. Sometimes Blackboard hangs up with that. You can't take any of the previous quizzes. Those are pretty much set for, the dead dates that they're on. Um, I haven't posted any extra credits. I didn't think anybody really needed them, judging on like the grade average of the class. But if anybody is interested in extra credits, shoot me an email. I can always come up with an odd assignment or two, even if it's something, like write a paragraph on this article or something like that. We could definitely do that, where I could give you points or something towards a grade part that you're concerned with. I've done extra credit for homeworks, quizzes, or labs. It's it would just be a different style of extra credit depending on what it's going for. But that's really it. And I hope you all have a beautiful rest of the week. Otherwise, if I don't see you tomorrow, if I see you tomorrow, then we'll go over whatever labs you may have. Or if you didn't finish the speaker model one, And I hope everybody had fun with that. It was very noisy, very noisy. No. but yeah, that's it, gentlemen. Yeah, and like I say, if you have no questions, I guess we'll call it. We'll call it. And I will see some of you tomorrow. And otherwise, I'll see some of you on Monday. All right. Oh, good Lord. Push that button and say unmute. No.
All righty, Tom, you have a good one.
All right, you too.
See ya,
See ya.
Tom.
See you, buddy.
See you on Monday, Tom.
All right. Oh, you got something, Will, or?
Forgot to click the button.
Oh, all right.